Welcome everyone to the first session of our seminar series on high throughput computing using Dask. My name is David Swenson. I'm one of the organizers of this event, this event series is organized by ECAM with assistance from CCAM. So at the beginning here, I'm going to talk a little bit about what those two organizations are. Then I'm going to move on to talking a little bit of background about what we mean by high throughput computing, by task-based computing. And then I'll introduce Jacob Tomlinson and Willy Rath, who are the people who are actually doing the real tutorial later on. So CCAM is the Centre Européen de Calcul Atomique et Moléculaire, the European Center for Atomic and Molecular Calculations. It's an organization with 50 years of experience of really bringing together the community of theoretical and computational chemists and helping us share information with each other through workshops, schools, and conferences. It's made of 17 nodes, mostly affiliated with academic institutions throughout Europe, with one also in Israel. The headquarters are in Lausanne, in Switzerland. ECAM is one of the European Union's Horizon 2020 Centers of Excellence. With ECAM, our mission is to help prepare the theoretical and computational chemistry community for sort of the next generation of supercomputers, looking at the exascale. ECAM is organized by 16 of the CCAM nodes, 3 PRACE sites, supercomputing sites, a Center for Industrial Computing, and 12 industrial partners. What we do within ECAM are we have these industrial partnerships where we try and transfer information from academia to industry. We do a lot of software development where we develop reusable and high quality software modules. And we do training where we teach people about both software best practices as well as specific tools that we think are interesting. Of course, this event falls into that last category. We think that Dask and this high throughput computing approach is a great opportunity. Today, you'll learn a lot of things that you can already do today to improve your data analysis, to facilitate the kinds of data analysis that would otherwise be more difficult to do. We also think that these tools are going to be important as an additional layer of parallelization, which will come in later workshops, later episodes of this series, because it gives us extra layer of parallelization that will help us reach the exascale in efficient use of computational resources. So what is task-based computing? What do I mean by that? So what you need to do when you're doing task-based computing is you describe your program as a set of tasks, where the output of one task becomes the input of another task. So I have a little example here that's pretty boring at the bottom. You have inputs in task A, the output of A goes into B, the output of B goes into C. We've probably all written very simple programs like this before, where each task may have been a function that we've written elsewhere, and then we just have this sequence of functions that we call, where the output of one becomes the input of the next. The thing to see here is that we have what you can think of as a network or a graph. So the tasks themselves are nodes, and you see the lines with arrows, the output becoming input of another. That is a directed link between these things. And of course, because no task can have as input its own output, we don't have time travel, it is an acyclic graph. So this is a directed acyclic graph. Again, the particular one that you see here is boring, but they can be more interesting, and they can be, in fact, quite complicated. One thing to notice in even this still relatively simple example is that as soon as we've finished task B, if we finish both task A and task B, we can work simultaneously on task C and task E. And figuring out what is available as the next work to do is the job of the scheduler, which will then handle the parallelization. What we'll be doing here is the scheduler we'll be talking about is inside of Dask. And we'll talk a little bit about how you can do this sort of thing with your own code, with your own arbitrarily complicated thing. You can use Dask, you can tell Dask what your task graph looks like, and then Dask will know how to execute it. But one of the great things about Dask is that in many cases, you don't even need to do that. If you're already using NumPy, Pandas, scikit-learn for your analysis, for your scientific work, Dask has tools that can often just be a drop-in replacement for those. And so you'll get the parallelization for free. It's very little work and it just does what you want. We'll see a lot of that today, these useful integrations. So again, this is the first of a 3-part series. And today we're going to talk about Dask itself. We're going to talk about these integrations, that core library, and essentially parallelization within one node. We're not going to push too far into how to do this in high performance computing. Next week, or not next week, but in 2 weeks, the next time on the 4th of February, we'll have Dask Job Queue. And that will teach you how to integrate Dask with the queuing system on your HPC cluster. So that could be Slurm, that could be PBS, that could be Grid Engine. And then finally, on the 11th of February, we'll have Job Queue features, which builds on Dask Job Queue to allow some more complicated workflows, like if you have MPI within your tasks, so you can do multi-node tasks. And this is really what we're doing when we're trying to push towards exascale computing using these tools. A couple of things, I think that the tutorial materials and the binder link are already available in the chats of either the YouTube video or the Zoom, whichever you're on. Feel free to ask questions during the tutorial through the chat. We will be watching that and bringing those up to the speaker at reasonable times. So with that, I'll introduce today's 2 speakers, or the main speaker here is Jacob Tomlinson, who is a senior software engineer at Nvidia. Prior to that, he had worked at the Met Office, the UK's meteorological service. Jacob is an active developer involved in Dask and the Dask community, regularly making contributions to projects with Dask. So it's really great to have someone who is genuinely an expert on this stuff here. And we'll also have Willy Rath will be helping with questions, especially. Willy is a research software engineer at Geomar, the Helmholtz Center for Ocean Studies. And in addition to being an expert on using Dask, Willy is an expert on the modeling of ocean currents. So with that, I will pass the floor over to Jacob, and it's all yours.
Thank you very much. Right, let me spend some time trying to share my screen now. Oh, lovely. Sorry, my machine is now asking me for extra permissions, which is kind of what I expected to happen. I knew I should have clicked this before when we were setting up. I may need to disconnect and reconnect. 1 second. Apologies for the delay.
Yeah, maybe while Jacob reconnects, Alan has posted for the people following in the Zoom on Zoom. I think Alan has posted links to the GitHub repository and an interactive platform to follow along binder in both chats, right? In the YouTube chat and in the Zoom chat. So with this.
There we go. Sorry, everybody. You always have these technical exciting things. Yeah. So as David said, my name is Jacob Tomlinson. I'm a software engineer at Nvidia. I used to work as a, I don't know, kind of like a research software engineer for the UK Met Office. So I've been working with Dask for, I don't know, maybe 3 or 4 years now. Most of my involvement in the group is in deploying Dask, dealing with the distributed nature of it. So kind of what we're going to be running through today is kind of an overview of what Dask is and how to use it and how the tool works. But Dask allows you to scale up from making best use of the machine that's right in front of you to making use of the best use of the cluster that you have access to, or the cloud computing platform that you have access to. And so I focus a lot on that kind of distributed side of things. But I'm going to start by kind of doing a bit of an introduction into kind of what Dask is and how it came about. I'm also going to talk a little bit about why I work for Nvidia and how Nvidia kind of fits into this piece. And then we're going to run through a bunch of the materials. So I think, as everybody said, there's this binder that you should be able to see in the screen share now. I've got the link down in the bottom corner. I think the link is in the chat as well. If you can all try and make sure you get, if you want to follow along, basically try and get yourself through to this point where you've got JupyterLab open. on the right-hand side, we have like a whole set of notebooks. I've got a couple of extra things in here just because I wanted to show you the link and stuff. But you should be able to see these 1 through 9 numbered notebooks. These are the pieces of our tutorial that we're going to be running through. I've got the intro notebook open. We're going to kind of step through each of these. Each one is kind of split down into a different category. Some of the parts of this tutorial, they're kind of steps for you to just follow along, and I'm going to be talking through. I'm going to be talking, a reasonable amount for the next 90 minutes or so, I expect. There's also a couple of lab sessions that I'll kind of leave you. You kind of have maybe, 10 minutes to try and work through those yourself. I'll be quiet. It will give you a chance to have a look through the lab or check your email or do whatever you want to do. I appreciate these sessions can be, can be reasonably long. So I'm going to I've got my screen reasonably large so that hopefully you can read everything well in the screen share. So I'm going to kind of collapse away my file browser on the side here. You can see a few things I've got open in my Jupyter Lab session. I'll kind of come on to what those are in a little bit. But at its core, Dask is a pure Python library to help you scale your workload out to improve performance and make better use of the computing resource that you have access to. So I've got a nice big bullet point list. I'm going to walk through these and kind of explain them a little bit more depth. So it's built in pure Python, which means it's kind of architecture agnostic. If you can run Python on it, you can run Dask on it. This is great for all the kind of various flavors of HPC systems out there. If you're an Apple laptop user, you now have multiple architectures to choose from. The fact this is built in pure Python means that this would just run kind of wherever you are. Dask can scale you up. I've personally run multi-thousand machine clusters for doing various operations. Dask will run a single kind of function call, a single execution across thousands of machines if you want to go that big for doing some kind of operation. But also Dask scales all the way down as well. Like I have a laptop here that I do most of my work on. It has 12 logical CPU cores in it. It's a reasonably modern i7 processor in it. And Dask can make use of all of those cores in my laptop as well. So Python typically is single threaded. If you're using some of the libraries, maybe they use lower level kind of multi-core to get some performance increase. But if I want to run some work, I want to make the most use of my laptop that's right in front of me, I can use all 12 cores for what I'm doing. And then if that's not fast enough, I can then go and grab some resource from somewhere else and scale up to hundreds or thousands of cores. So because in that intro, it's really great to see kind of an overview of how task-based computation works. And we'll get to that in a little while. But one of Dask's kind of, I think, core selling points is that you can make, if you already know NumPy and Pandas and scikit-learn or parts of those tools, you can make use of Dask without having to worry too much about how the distribution is working and how the task-based computing is happening. A lot of Dask's libraries follow exactly the same API as NumPy or Pandas. Your work can look exactly the same. There's maybe some extra keyword arguments to kind of deal with some nuances of doing distributed computing. But if you're familiar with some of those existing tools, then Dask should seem familiar to you as well. Dask tries to adhere to the Zen of Python rules. So that's kind of hopefully just creating quality software. Now, let's actually have a look at some Python code as we dig into this. So this little pattern here in this first notebook cell, you're going to see me using this quite a lot. And this is it's not necessary all the time, but I just kind of want to get you used to the fact that Dask uses a distributed scheduler in order to split all of its work up and spread it across wherever it is, whether that's on my laptop, whether that's on a big cluster. We're using this distributed scheduler. And there's a whole bunch of tooling within Dask for building clusters and setting things up like that. But this minimal example here is creating us a small Dask cluster, which is exactly the size of the resources that Binder has given us, right? So I think by default, Binder gives you maybe two CPU cores and 2 gig of RAM. So we've kind of split this out here. From Dask distributed, we're importing client. We're making ourselves a new client here. So we're going to connect to a distributed cluster. This actually happens to have a side effect of creating the cluster in the first place as well. But we're going to say we want 2 workers. Each worker is going to use one of those CPUs and 1 gigabyte of RAM. And if we run this call here, we can inspect this client object and see we've got what we asked for, right? We've got 2 workers, 2 cores, 2 gig of RAM. You can also see on the right-hand side, the Dask dashboard has also sprung to life. So we'll come into the dashboard kind of in depth later, but the Dask, because Dask scheduler is handling all of our tasks and handling all of our computation, we can get some insight into what is happening from like a performance point of view, from all the different aspects of what our code is doing. And Dask has got some nice kind of browser-based web pages that you can have a look at what's going on. And it's also got a Jupyter Lab extension, so we can see them here on the side. There's also a Dask icon over here on the left of my Jupyter Lab, and if I click that, I can see I've got a bunch more plots that I could look at if I wanted to. I'm going to kind of leave that for now. We'll come on to that later, but I now have a Dask cluster that I can do some work on. So the first thing I'm going to do is I'm going to import Dask data frame. Now this is the Pandas kind of sub API in Dask, if you like. So using Dask data frame is exactly like using Pandas. Most of the function calls are exactly the same. Most of the keyword arguments are exactly the same. The documentation will kind of point you at any differences, but generally it's a drop-in replacement for Pandas. So here we're going to read in some data. This binder has got like a bunch of data kind of here. These are small open data sets that we're going to play around with a little bit. So I've got a small beer data set here. And what I'm going to do is say Dask data frame, read this CSV file in. Now, one difference is I'm going to specify a block size. And what I mean by that is I'm going to read the CSV in pieces rather than as a whole thing, right? If you're doing this in Pandas, you would read this data set fully into memory. And if that data set was bigger than the memory of your machine, then tough. With Dask will read in whatever data set you want in pieces, in chunks. Sometimes they're called blocks, sometimes they're called partitions, sometimes they're called chunks. The names kind of come up a bit, but here we're saying this is in bytes. So we're saying, please read in the CSV file in these chunks. If I run this call, it'll read this data. And if we just have a look at it, we can see this Dask data frame structure. Now what's happened here, this should look familiar if you've used Pandas before. This is like a notebook representation of a data frame. And you can see we've got our column headings along the top, right? The brewery ID and the brewery name and all of that. This is, review data on beers, I think, from breweries. But you can see the data is missing here. We've got some data types of our data, but we don't actually have any data. And we've got some extra information here that Dask has given us. So we have 2 partitions and 2 tasks. And what that means is Dask has read in the CSV file and split it on this number of bytes, and we've ended up with 2 chunks, splitting the CSV file up into 2 chunks. But Dask hasn't actually, it's had like a peek at the file. It's looked into the header to try and work out what the column names are and the data types, but it's not actually read our data in. And this is really, really important, because if you have like a multi-gigabyte or multi-terabyte data set, you don't really want Dask to do anything until you absolutely need to. So we have this concept of like doing just-in-time calculations, lazy calculations. There's a few terms for it, but here we've read in this, and Dask has said, look, there's 2 chunks here, there's 2 pieces, and if we do some things, then we'll have to operate on those 2 tasks. But those 2 tasks are 2 separate read calls. So we have a nice diagram here to kind of explain what's going on inside. We have our Dask data frame object, which represents all of the data that we read in from the CSV file. But each of the chunks, each partition is or will be, should I say, a Pandas data frame of its own accord. But it's kind of represented by this higher level Dask data frame object. So if we do things to our data frame that we've loaded in here, Dask will ask Pandas to do some operation for us, and then it will aggregate those results and kind of give it back to us as a single view. And this is a lot of what Dask does under the hood, is kind of splitting things up into tasks and chunks and pieces, and then actually handing the work off to downstream libraries to do some operations, and then kind of aggregating things back together for simple operations. So I could do something like a map across my chunks, my partitions. So there's a Dask call here called map partitions, where we pass it a function and we say, Dask, please run this function on all of my partitions. And if I just get rid of this for a second, if I run this, we'll get back another Dask structure, which is saying, this is what would happen if I ran type on these partitions. Again, it's not giving us any information because everything in Dask happens kind of just in time. It happens lazily. So this is building us up a nice big graph of futures of all the things that we want to calculate and all the things we want to do. So in order to actually make Dask do something, we need to try and look at the result. And there's a few different ways of doing that. There's a few operations in Dask that do that implicitly, but a lot of the time you'll see this .compute call on the end where we explicitly say to Dask, do the thing, right? We've built ourselves up a big graph of whatever operations we're going to do, but please now compute that graph. So if I call this with compute on the end, we should get back a series where we've run type on each partition, and the type of each of these partition is a pandas data frame, right? This is regular pure pandas underneath, but Dask has kind of wrapped those up for us. I can do standard operations that I would do in pandas, like I can call head on our data frame, which returns you the first 5 rows of a pandas data frame. Doing that to our Dask data frame, we'll read in the first partition and then call a head on that and then pass it back to us, right? It does just enough work to get us to the point that we'd need to do. This implicitly has calculated this for us. There's a few things. I think if you call length on a data frame and head and a few other operations, it will implicitly compute for you. Other than that, you have to compute yourself. But you can see a little bit of the data here. We have breweries, we have a review score of the different beers, we have the beer style and the beer name, and a few things from this little toy data set. So we can do things that would feel familiar if you're used to pandas. So we could filter our data frame on all of the beers where the beer style contains the phrase IPA, right? So if we want all of the IPAs, we can do that kind of filtering. And we've called head here just so we can kind of inspect that again. So I think my task stream is not doing anything. Let me just reload this frame a second. We should see activity on this. Yeah, here we go. If I run this again, we should see some activity over on the side where this task stream plot represents our 2 cores. There's 2 rows here representing our 2 cores of our machine. And each of these little bars is representing some calculation that happened. Now, I haven't done very much calculation, so this doesn't look very interesting at the moment, but hopefully we'll see some more of that later. But we can do something like assign, filter our data frame by IPAs again, but assign this to a new variable called IPA. And then we could do something like group by the brewery name and then get the overall review of the beer and aggregate it by mean and count. So if I call this again, all of this is happening lazily. So if I just have a look at this mean IPA review variable, this is just another one of these kind of uncomputed structures that Dask has built up for us. And it knows what the shape will be. It knows what this will look like. We'll have 2 columns called mean and count, and the rows will be our beers, I think, or breweries. And Dask also knows that it will take 12 tasks in order to calculate this, right? It's building up this graph of things that needs to do in order to get to this point. It knows that there's 12 tasks required to get here. So if we call compute now, those 12 tasks will be executed by our scheduler, and we'll get our output. Now, all of this stuff is happening very fast on this small data set here, but we can see our brewery name down the side, and we can see our mean review score, and we can also see the count, of number of reviews of that brewery. And you can carry on doing standard pandas stuff. So if you want like the 20 largest mean scores, we can do that call, and it will show us, okay, these are the best breweries within this data set. But if you look at some of them, some of these breweries have just got 1 5-star review, whereas some of these have actually, this one's got 400 4.5-star reviews. So maybe you want to do some filtering. Maybe you want to do, this is kind of how you would dig into doing your data science workflow on this table of data here. Now, having all of this data in CSV is great. I can work on this locally, but typically we will want to work with some kind of distributed data set or some kind of data set that is stored in some way that's not just in my local system. So Dask has got a bunch of reading, writing operations for reading in different types. Some examples here, we can read and write CSV, we can read and write HDF, we can read and write JSON, we can read and write Parquet. There's like a whole bunch of things you can look at here. But because everything's been split up into pieces and we have partitions, reading and writing gets slightly more complicated, right? Reading is fine. We can kind of, we have a bunch of files, we can read those in kind of blocks and chunks, but writing becomes complicated. I have 2 workers in this case, but maybe I have 1,000 workers in some other workflow. If I have some data where all these workers are going to do some work, they're going to calculate something, they're going to keep some data in memory, and then I want to write it to disk, I have 2 choices, right? I can either aggregate all of that memory in one place and then have that memory written to disk, or I can do like a parallel write where every worker kind of writes a piece of its data into some kind of distributed format. Now, Dask has support for like a distributed CSV format where we can do something like write a CSV file that is named IPA-star.csv, and Dask knows that the star here should be replaced with the partition number. So if we have multiple partitions of data in memory and we want to write it to disk, I can call this and it will write out multiple CSV files. This mean IPA review data set was so small, there was only one partition. So it's written out an IPA0 file. I think I can go to the browser on the side and see, I have this file here. But if this was a larger data set made of multiple partitions, these would have been written as multiple files to disk, kind of, written concurrently by my cluster. This is great on like an HPC system. If you have access to some nice fast storage, you can have multiple machines reading and writing to disk at the same time. Now, the last thing I'm going to do in this notebook is close out this cluster. Now, typically you don't have to do this all of the time. Dask will try and close things out for you as you kind of exit your notebook or exit your Python session. But it's a good habit to be in, to just say, I want to close, I want to disconnect, I want to shut down, I want to stop. You can see my dashboard over here is reset back to the placeholder tabs. I'm mainly doing this here because as I run through the tutorial, I'm going to be creating and destroying different Dask clusters. So I recommend whenever you get to this point, hit close. So there's a bit of history here about kind of where Dask has come from. I'm not going to kind of go through all of this, but one of the things I want to say is Dask grew out of Anaconda, which is a consulting company based around Python data, PyData ecosystem. But Dask is contributed to by a whole bunch of people. I previously worked for the Met Office in the UK. I was doing work with weather and climate data. We needed a way of operating on distributed data sets in Python. Dask seemed like a good fit, and so we started working on that. But there's a whole bunch of companies out there working in this ecosystem, contributing to this ecosystem. And just to take a slight diversion from the tutorial for a second. So I'm employed by Nvidia, but I work on another open source suite of software called Rapids. And Rapids is akin to Dask. Dask is actually like a component of Rapids. Like Rapids is a suite of different Python libraries that are useful for a variety of different things. And the primary thing that Rapids is trying to achieve is to take familiar Python APIs that the ones we've discussed already, I guess, NumPy and Pandas and scikit-learn. And instead of accelerating them by distributing with Dask, we're accelerating them by moving the computation onto a GPU, right? There's kind of alternative libraries that have been written in optimized CUDA code, which allows you to execute the same kind of operation using the same Python APIs, but it just goes a lot faster on an Nvidia GPU. So if you're used to using NumPy, you can switch over and use CuPy. If you're used to using Pandas, you can switch over and use cuDF. And so you get some nice, we call this vertical scaling, right? You use a more powerful processor, you can get some faster computation. But Rapids also wants folks to be able to use multiple GPUs. And this is where Dask kind of comes into this, is you can swap out NumPy or Pandas for CuPy and cuDF, but also you can use those with Dask. Dask doesn't necessarily, in this example, we had Pandas as our kind of internal object, but it doesn't have to have Pandas as our internal object. It just has to have something that is Pandas-like. So Dask can also work with cuDF as its internal structure. So you can then have a distributed GPU accelerated data frame where you have a whole bunch of data on a cluster of machines with NVIDIA cards in. And so you get both benefits. You get the vertical scaling of using faster hardware, and you get the horizontal scaling of using many of them at the same time to do some distributed operation. So I'm employed to work on Dask in the open source community and make it better, make sure it integrates well with the Rapids ecosystem, and just generally make it good for folks. So I recommend you go and check out Rapids as well as Dask. It might be a good way to kind of get some performance increase. But I'll jump back to the Dask tutorial now and kind of carry on chugging through this. So I appreciate I'm kind of running. I've kind of slowly walked through this intro intentionally, and that's I'm going to kind of pick up the pace now as we go through. So one last bit of housekeeping here. I'm going to shut down the kernel of my notebook here in this little stop tab on the side. And then I'm going to open my second notebook, which will start a new Python kernel over here. I'm just trying to keep things neat. I don't want to get into a muddle as I'm running through this of kind of doing the wrong things. So this is the first bit where I stop talking for a minute and let you kind of absorb everything I've just said, maybe have a break for a second. But this second notebook is a lab exercise which will basically ask you to run through the same thing, but on a different data set. The actual calls here will be almost the same as the previous notebook, so please refer between the two, but this will kind of talk you through doing that second section. So I'm going to leave this up on my screen. I'm going to stop talking for the next 10 minutes. So it's 1:30 now. So at 22, I'll kind of pick up and carry on. Please have a read through this, have a read through the first notebook. And if you have any questions, kind of ping me in the chat. And I can try and answer them as we go. But yeah, I'll see you in 10 minutes. One thing that's often fun at this point, kind of as we're working through labs, if you want, head over into the chat and send a message just saying hi and maybe your first name and where you're watching from. It's always nice to just see kind of where people are tuning in from for this session. It's always nice to kind of read through names as well and say hi back. I'm just trying to work out where the YouTube chat is. I can see the Zoom chat here. So hi, Alex in Boulder, Ali in Leon, Nick in Basel, Thor in Amsterdam, Hannah also in Amsterdam, Adam in Wroclaw. Thank you all for joining. It's always nice to kind of have an idea of who's on the end. It's really weird presenting a tutorial like this, actually, because you're kind of presenting into the void of the internet, hoping that it's useful for folks. So yeah. Thanks for sending the messages. I'm going to try and find the YouTube chat now as well.
On the YouTube chat, we have somebody from the Netherlands, one from Austria, one from Ireland, one from Kiel. I think that's it. So
Cool. Well, hi everybody. Thanks for saying hi. There's a few more people saying hi in Madrid, and more folks in Kiel, more folks in Lyon, Germany, Vienna. It's good. It's very nice to see you all. So we're about halfway through this lab session now. So yeah, another 5 minutes, and then I'm gonna run through the solution to this notebook and kind of show things. If you have any trouble, if you get stuck in any of this, please do give us a shout in the chat, and we can help you out as we're going. Okay, right. I make it 22 now, so I'm going to move on to the next bit. If you've not finished the lab, don't worry, we're just gonna kind of run through the answers and have a look at this all together. So I don't think I've actually done anything in this, but I'm gonna try and be good and clean up my notebooks as I go. So we've got a solution here. It's basically the same operation we were doing before, but maybe with a few extra steps at the end. So the first thing we're going to do is going to create our Dask cluster on our binder session. So we have, again, 2 workers, 1 core, 1 gig of RAM, and we're going to read in a CSV file. But this data is not comma separated, it's space separated. So we've had to use the sep operation, kind of given in this hint before, and we're going to do the same thing with reading in the block size. So this call is basically the same as before, except we're specifying this is space separated. We're also going to rename some columns. We can do that by directly assigning our columns a list of new column names, and we can also drop our column here as well that we don't want, the X column. So we now have our project, our page, and our requests columns. Next, we want to do is filter our project for English Wikipedia. So we want to filter on the EN locale. So this is the same as you would do in Pandas. We're going to use square brackets to do like fancy indexing basically, and we're going to give it if you've not used Pandas before, this is here evaluates to like a Boolean series, right? So we say project, this is a series, a single column of our data frame from the project column, and we're going to say, is this equal to en? Instead of giving us like a true or false value like you'd expect, this actually gives us a series of true or false values, where it's compared like each element with that string. So this gives us a Boolean series, and then we can use that to filter on DDF here. So if we have a look at the output here, I'm kind of keeping hold of all of the previous versions here. So we've got DDF3 now. This looks the same, but you can see we're building up multiple tasks here. So each time we do this, we had 12 tasks before, now we have 24 tasks, kind of doubling the work each time. And now we can say, well, let's have a look at how many, from DDF2, how many pages do we have altogether? So we're going to call count on our whole data frame and compute that. My task stream keeps not working. I think there was a bug in the Dask lab extension that we fixed, but I don't know if Binder's like picked up the newer version here. So things aren't showing in my task stream very nicely. And you can see we've got, what's this, just over 1 million pages here. There we go. You can see the task stream doing something this time. So you can see each one of these is kind of our reading our CSV operations, these big blue ones. And then we have our like smaller operations, which are all our kind of renaming and filtering and aggregating and that kind of stuff. All of these are color coded, right? So the same function call on a different chunk of data in memory, it will be the same color to try and help you see what we're doing. So the thing that took the most time here was reading the data from disk. You can see we've got 196,000 things. Now there's an extra credit section here, which was just saying what are the record counts for all of English, French, Chinese, and Polish. So we can use is in, where we say, instead of saying, is this string equal to this string, we can say, is the string in this list of strings? Is it one of these options? But in order to do that, we need to reset our index in order to do that. All of this stuff is kind of covered in the documentation. These are some of the nuances you come across by having these distributed data frames. And hopefully you can see the task stream do something that time. So you can see we actually get like an output here where we get some kind of nice results. So hopefully you're able to follow along with that. If not, don't worry. I'm just going to keep clicking through. Like none of this kind of builds on anything. We're just going to go through each operation. So don't worry if you didn't kind of finish through to that point. So I've closed up my cluster again, just to reset my dashboards. I'm going to come over here and shut down my notebook. And I'm going to move on to number 4. Discard that. So this one here, we're going to go through the same thing again, but what I want to focus on this time is these dashboards in a little bit more detail of actually looking at what is going on within Dask. So I don't really care about what my work is doing at this point. I just care about how I can see how it's doing it. So let's create another cluster again. Just this is how we start every one of our notebooks in the tutorial. We're going to create this cluster, 2 workers, 2 cores. Now, this is great, and we can see these things over here in Jupyter Lab, but this is kind of giving us a view onto a full dashboard. So I can find this. If I head over to the Dask tab here, this URL at the top is the URL of where the dashboard is. Now this is a relative URL, right? There's nothing at the beginning. It's just saying relative to where I am here, this is where my dashboard is. So what I'm going to do, I'm going to pop open a new browser tab. I'm just going to mush these two strings together. So that would be relative from the domain like that. Oh, I didn't like that. That's a shame. Let me, I think, yeah, I know what that was. That is because when you head to the Dask dashboard, sorry, I'm just going to fumble around with this for a second. All right. This here is the URL of the dashboard, but when you hit the homepage of the dashboard, it redirects you to a page called status, and I think that redirect is maybe just a little bit broken there. Excellent, that's better. So this is kind of the pure Dask dashboard. Now, the way that we're doing all of the things in these notebooks is we're using the Dask distributed client from within our Python session, but there are many ways of deploying Dask clusters. And we'll kind of come on to some of those later. But one of the most basic things you can do is in a bash terminal, you can run Dask scheduler, which will start a scheduler. Then in another Dask bash terminal, you can run Dask worker and give it the IP address of the scheduler, and they'll pull together. And if you ever want to see what's going on in a cluster like that, the Dask dashboard will run on port 8787 on whatever machine the scheduler's on. Now, because we're doing this in JupyterLab and because we're doing this in Binder, all of this stuff is being cleverly proxied around and forwarded so that you can get access to this. But if I was to run this on my machine, just run Dask scheduler, I would go to localhost 8787 and I would be able to see this web page. So you can try that out for yourself. Now there's like a whole bunch of tabs along the top here. This is the main status page. We can see what's going on. I can hit the workers page, which is a view on, we already had this view over here in JupyterLab. This is giving us a list of all of the workers connected to our cluster and a rundown of those things. So how much CPU are they using, memory, IO, those kind of things. We can have a look into tasks and see our task stream. This is the other plot that we had here, which is kind of showing us a time series as we go of what tasks are being executed. We can grab system information overall about the scheduler and how the scheduler is performing. We can head into the profile page. Now this, let's run some code and we'll have a look at this. So let's do this. This is just a lump of the code from before, right? But I'm going to do this. I think we need to compute it as well. If I compute this work here and then head back to this dashboard, I think I need to hit update here. Right, we can see it's called a flame plot of what happened within our execution. So the bar at the bottom is our cell that we ran, right? We called compute, what happened inside of that. The next level up is these are the functions that were called here. So we had read blocks from file call. We had a pandas read text call. This is kind of where it's parsing the CSV. We had some Python internal calls as well. We had an apply and a save size of, right? So these are some internal calls that happened within Dask. We can then go up to the next layer and see, well, this pandas read text, what did that do? Or that called read CSV. And what did that do? That called read, and that called another function called read. That function had some other bits and pieces in it. And this is kind of useful for seeing where bottlenecks are in your code and trying to, look at what is taking the time within my operation. I ran this compute. We had to wait for a couple of seconds. What took that time? And, we can see here it's this pandas read call, reading that CSV file in and parsing the text. Is the thing that took the bulk of the time, actually doing the kind of aggregations. And you can see we've got some drop calls in here. This is where we're dropping our columns. And then this is where we're checking whether it is null values, and we're doing some reducing and things, right? But we can see a big chunk of it was reading in our text. A big chunk of this actually reading with pandas read CSV is doing type inferencing. Right? Data stored in CSV is just string data. So knowing whether it's an integer or a string or a date or whatever, Pandas has to do a whole bunch of inferencing on that. So to just take off my Dask hat and put my Nvidia hat back on again, GPUs are really good at doing this, doing type inferencing on strings, which is not something, if you're into GPU development, it's not something you typically consider to be a good use of a GPU, but it is. We have some cool libraries now which can do this kind of stuff. So doing the same operation with QDF, this read CSV line is a lot faster in QDF because it can distribute this type inferencing. Anyway, I take my Nvidia hat off and put my Dask hat back on again. So we've got this dashboard. We can look at the profile. We can look at the graph. I think this should show us it shows us what is executing. I'm just going to call persist here. So this persist call is a lot like compute, except it says keep things in memory. Instead of just giving me the answer, please hold this in your scheduler brain for a little while. So we can see our graph has kind of popped up here. These is our acyclic task graph. Basically, we have 4 read CSV calls here. And then each one of those, we did a count, I think, in this operation. I didn't actually read what it does. Yeah, we did a count here. So we have 4 separate read CSV calls. And then on each of those, we have 4 separate count calls where we'd like doing a count within each one. And then we kind of reduce all of that together into a final, aggregate those counts into a final count call here. So we can kind of see how that's been chunked up and how it's executed over time. As you run more complex workloads, this plot gets way more complex, and you can kind of see what's taking time, where things are blocked, where things are waiting, what tasks are waiting for what tasks. So it can be very useful for tracking down how your workflow is running. We can also see this from the notebook end. So let me collapse that again. Instead of calling, we can call persist to run the work and have a look at this dashboard, but we can also call visualize. And this will give us a nice representation of that same graph, but with the same kind of information in it. So you can see at the bottom here, we've got our 4 read CSV calls, we've got our 4 column rename calls, we've got our 4 drop column calls, and then we've got our 4 count calls and a count aggregation, and finally you get your result at the top. So in these kind of graphs, you can see this is your acyclic task graph. Each of the circles is a function that's being called, a task that's being operated on, within Dask. And each one of these squares is a piece of memory that's being held. Now, memory is kind of held and freed as it's needed. If we look at the graph here, we can see these were calculated and then released again. They've gone blue, but its final result is red. We're holding this in memory because we care about this. We care about this answer. So this is really useful for seeing what's going on. We can have a look at some more complex ones. Like our third data frame was to filter down by English. So you can see if we visualize this graph, there's like some extra steps where we're saying, after we've dropped our column, but before we do our count, do some equivalency check, right? Is this string equivalent to the en string, right? So there's like some operations here that were extra operations that were required. What was that? Yeah, that's the answer. And yeah, I've run through slightly out of order in this notebook, right? We've already had a look at the profile, so we can see kind of what was going on and what was taking time in there. We've got a little lab exercise here. Let me just have a look at how I'm doing. I'm gonna keep going because I'm kind of roughly on time. But you can kind of have a poke around with this kind of as we come through the other lab sessions. So I think I'm just going to close out this cluster. No, actually, before we move on, I'm just going to have a look at, we've looked at all of these things in the Dask dashboard. This is the traditional web-based Dask dashboard. The last thing I kind of want to show you is how to do this all in Jupyter Lab. So we have our link to our Dask dashboard. This can actually be any Dask dashboard. And we have a little search icon here, which hunts for a Dask session within your current notebook and can like pre-populate that for you. So if this is blank and you have a Dask cluster in your notebook, you can often hit the search and it will find the right endpoint for you. But we have all these orange buttons which represent all of the plots here. And lots of these are kind of broken down. So if you look at the status page, we have bytes stored, tasks processing, the task stream, and our progress bars. That's actually 4 separate plots. And Jupyter Lab, we can grab each of those kind of separately if you like. So we can get our progress plots, right, our progress bars, and move them around and readjust things. We can get our number of bytes that we're storing in memory on our workers. I personally always like to have the task stream down at the bottom. I'm going to close this binder link now if I hope nobody minds. I think it was linked in a few places. I tend to not look at the Dask workers plot. I like n bytes, I like progress, I like the task stream. There's quite a few different things you can look at. I like cluster plot as well. So if I kind of collapse this and restructure myself a little bit, I can see my tasks that are being operated on over time down the bottom. I can see my memory usage of my cluster. All these plots look slightly strange because I've zoomed in and made everything big for the purpose of the stream. But the text generally fits in these boxes if you have everything at 100%. But this other plot here, this is the Dask cluster map. This shows you like an overview representation of your cluster. So the big purple ball in the middle is your scheduler, and the two orange balls either side are our two Dask workers. We can, if you have more workers, they'll be kind of arranged in a ring around the ball. And if I call, let's call compute again. Compute. I call compute again, we should see a bunch of stuff happen. Oh, we've persisted, so it's forgotten about. It doesn't need to do anything. Let's do ddf3.compute. You can see like a bunch of stuff happening, right? Hopefully you saw the cluster map. The scheduler will have fired some little tasks out to the workers. The workers kind of change color as they're processing those tasks. And then if they need to communicate, like in this count, they do a bunch of separate counting, and then they have to aggregate the result, which means that all the answers from each worker has to be passed to one place in order for that to happen. That is represented by a dashed red line. So this can be really helpful to see how busy are my workers, what are they doing, how much are they communicating with each other. The task stream down the bottom shows this. You can see the little red line here. This is transfer. This is memory moving between. But the cluster map just kind of gives you like a bit more of a feel for how your cluster is laid out topographically. So I think that's it kind of for this notebook. I'll stop rambling a bit about that. Let's close out the Dask cluster, and we'll move on to the next notebook, which is Dask array. Now, in the setup, Willie, I think you said this is a good point to kind of stop and check if anybody has any questions, because we're shifting topic a little bit here, right? We're moving on to some other stuff that you can do with Dask now. So yeah, if anybody has any questions about data frames or dashboards or anything like that, it might be a moment to just ask in the chats. I'll kind of give you a minute to kind of gather yourselves as well.
Yeah, there was a question in the Zoom chat on about in-place modification of Dask data frames, right? They to some extent they behave like dictionaries. So you can, if you want to drop a column, for example, you can just delete the column from the dictionary like Dask data frame. But there's also command line arguments to the drop method that allows for an in-place modification of the Dask data frame. Now, I would be interested in, Jacob, if you generally would recommend in-place modifications over explicit new assignments. I note that I don't do this anymore at all because it gets you in all kinds of trouble. But maybe I'm in.
Yeah, I typically don't do in-place ever, and I think in-place. Some languages do things in certain ways, and in place feels like really natural to some folks. Whereas like I prefer to be really explicit, right? Like when I call a function, that function is gonna output something, and I therefore need to assign that somewhere. I need to keep hold of that. And if that is kind of overwriting the same thing, then I feel like that's fine. But I feel like I'm being very explicit about, I'm replacing my variable with a new thing, which is probably my variable with some function call. And I feel like I'm chaining my graph together at that point. If maybe I have a cell which is kind of got a bunch of function calls all kind of chained together, with dot this call, dot that call, dot that call. That all kind of feels like I'm constructing my graph. Whereas in place, I feel like I don't know, I can get into trouble sometimes, like you say. So yeah, I feel like a best practice is to not use in place, but at the same time, we support both. So do what feels natural to you. Okay, given we haven't had any other questions, I think we'll just carry on plodding along. So the next thing I'm going to talk about is Dask array. Now, this everything we've done so far, we've basically been thinking about the pandas-like functionality of Dask, which is great if you like pandas. My background, I come from weather and climate. I basically never use pandas. Maybe sometimes for I remember doing a project on river heights where I had some big CSV files of river heights recorded over time. Pandas was super useful for that. But most of the time I used to work with large multidimensional arrays of weather and climate data. So I'd be working with NumPy, and Dask has a NumPy-like API called Dask Array. And so we're going to have a look at kind of the differences between that and the Pandas implementation, and how we can run through. So the Dask Array API feels exactly like the NumPy API. And the idea is the same, right? So we've got another picture here. Before we had our Dask data frame, which represented a bunch of Pandas data frames. And, Pandas is a columnar data format. And so each one was, the same. Each partition had the same columns as every other partition because it's a table of data. Whereas in a big multidimensional array, I think the data sets I used to work with typically had maybe 6 dimensions. You have like latitude, longitude, altitude, weather has 2 time coordinates, and then you might have like variable, and you might also have ensemble. So you maybe have seven dimensions to your data, and it's a dense array of, high precision floats or something. So being able to represent that in a data frame doesn't make sense. You want to use some kind of array representation. So Dask does the same kind of thing. It splits out your Dask array into smaller NumPy arrays, but along the dimensionality that you have in your data. So, for a 2D data set, we might have something like this, where we have a Dask array that's made up of NumPy array chunks. But let's have a look at that more in depth. So let's make ourselves a cluster. And I'm going to import NumPy, and I'm also going to import Dask array. Okay, so you saw this time some of my other plots sprung to life. My scheduler started up and my 2 workers came along. So I import NumPy as NP and Dask array as DA. These are typically, they're not quite interchangeable, but they are, like things work exactly the same. The function calls are exactly the same. Maybe like there are some nuances to the Dask stuff, but typically I personally, with both Dask data frame and Dask array, I just read the Pandas documentation and read the NumPy documentation and try stuff. And most of the time it works. Sometimes I need to specify something like block size and things. But if I make myself a NumPy array, let's arrange some numbers, and we're going to make a 3-dimensional. No, we're going to make a 1-dimensional array. So we're going to go from 1 to 50 in steps of 3, right? So we get 1, 4, 7, etc. Right? We've got this 1D array of data. I can do exactly the same in Dask, except I specify my chunks here. Now this is, when I say chunks, I don't mean split this into 5 chunks. I mean split this into chunks of 5. And I can have a look at that. Now Dask has got this nice kind of representation because we've done exactly the same thing we did before, right? We haven't called a range yet. We haven't done any data, like we haven't got any data, nothing's in memory anywhere. We've instead constructed a graph that says, if I were to do this arrange operation, this is the functions I would do in this kind of graph. So, I have an array, which would be 136 bytes in chunks of 40 bytes. The shape of the array overall is 17 elements in 1 dimension. Each chunk is 5 elements in 1 dimension. And we get 4 tasks, 4 chunks. They're int64s, and the underlying data format, the underlying library is a NumPy array. You can also swap this out for CuPy if you're doing CuPy arrays. If you get into more exotic stuff, also there's another library called Pint, which has got kind of unit awareness. So you could have like a Pint array in here that's maybe in Kelvin, and it allows you to do conversions to Celsius or whatever. I could also do visualize on this, so I can see application's not working. I'm sure it's visualize, or maybe it doesn't. Can't remember that call. I'll come back to that. But yeah, you've got this overview representation of what this Dask array looks like. I can do things like have a look at the D type and the shape. These are the same things from the repr. So if you're not in JupyterLab, you can. Okay, somebody's just asked in the chat quickly, I didn't grasp the chunk concept. Could I elaborate? So yes, let me rewind a bit. When we read in our CSV files before, we said read these CSV files in blocks. So we got like pieces of our CSV file read as separate tasks into our overall data frame. We're doing the same kind of thing here, where we're saying, we want a Dask array. Yeah, I just don't think I can type. Thank you for giving me the answer there. I'll type that in a second. But yeah, the overall array here is one large Dask array made up of smaller NumPy arrays. So when we create a Dask array in the first place, we need to tell it what are these, how big are these chunks? What are these chunks? How do I make these? So in our NP arrange, we're saying to NumPy, please make me an array that looks like this. So for Dask, we say, please make me an array that looks like this. And your chunks will be of this shape, right? This is actually a shape here. I could specify this as a tuple as well. That may make it a bit clearer. Because, if I have a 2D array, I might say I want it a 5 by 5 chunks, or a 3D array, I might want 5 by 5 by 500, shaped chunks, and it will give me, it will kind of break my data up into those pieces. I'll carry on going, and we'll see kind of where we get to. Let me just copy that little snippet into here. Ooh, why did that not copy that? There we go. Right. So we can see here, in order to make up our Dask array, we need to call a range 4 times because there are 4 chunks. Each one of those will be like slightly different inputs in order to construct our overall Dask array of each of those chunks, right? This is like a tiny toy example. It makes more sense when you think about, I've got a terabyte of data. I have, a node in my HPC cluster, which has 64 gig of RAM. I want to load the whole, I want to load my whole terabyte of data. So I specify a chunk size that will fit inside the memory of my machine, basically. Maybe it needs to be much smaller than the memory of the machine, so we can have kind of swapping around space and scratch space for calculating and all that kind of stuff. So we can have a look at, this array has a chunk size of 5, which is what we specified before. And we can also say, like, what chunks do you have? And it's like, well, I've got a chunk of 5, a chunk of 5, a chunk of 5, and then I have a chunk of 2 because there's only 17 elements in the overall array. So I can't, I haven't got a complete chunk. It's okay to have incomplete chunks at the extremities. Within any chunking scheme within Dask, everything is regular size apart from the last chunk, which can be smaller. And then I have my visualize call here. This is just what I'm doing because I'm skipping ahead of myself. I can do other things. I can say, I can take my Dask array and I want to square every item in my Dask array. So this is exactly the same as arranging my data, and I get my output from arranging my data. But then I'm also going to call pow in NumPy on each of those to get like another output from there. And I can compute that and see all of my answers, right? So this is all of those numbers squared from in that array. And this has given me back a NumPy array, and I can check this by calling type on here. So this, I've calculated these 4 separate arrangements. I've squared each element of those arrangements, and then Dask has aggregated those as it's come back to my notebook session. And I can check the type, and it's like, no, this here now is a NumPy array. This is like my final output, my response. Your result may be a single number. If you're trying to calculate something, your result may be a plot. If you're trying to visualize something like that, Dask will try and hand it back to you in some sensible format as you're trying to get the like final answer. Now Dask array supports like a whole bunch of standard NumPy stuff. You can add things, you can multiply things, you can call sum and mean, and like very standard built-in Python functions. You can transpose stuff, you can do slicing, you can do fancy indexing. You can use ufuncs. All of these things are kind of supported within Dask. It knows if you call sum on a large Dask array, that it actually needs to break that up into a whole bunch of sums on each chunk and then do some aggregation step. Dask kind of will handle all of this for you. So you can do things that feel like normal Python. We can also do this with our, like blocked algorithms as well. So if I get like a random Dask array, this is, a similar kind of thing. I'm just saying I want an array that's 20 long in chunks of 5. I can call x.sum, and this will give me, instead of giving me the answer straight away, because I haven't called compute here. Remember, we have to call compute on these things. I've called x.sum, and it says, well, what I would give you back in this case is a Dask array that has no shape because it's just one number. It is just the sum of that thing. There are 9 tasks required in order to calculate this answer. I can visualize that result if I want. So we would call random sample 4 times. We would call sum 4 times. We would call sum aggregate in Dask, and we would get our final answer. So we can kind of have a look at what our code would do, and then we can call compute to actually make it do it. And we get number 12. Dask supports huge chunks of NumPy, so we can do all sorts of stuff. Let's make this example, we're making a 2D array here. So we're going to say this is we want it to be 15 by 15 in chunks of 10 by 5, right? So we've got slightly irregular chunk size, which is fine. We've got some incomplete chunks at the bottom, which is fine. But then we could do something like, well, I want to take this array, add it to its transpose, and call sum on the whole thing, right? We're just using NumPy syntax here as if this is a NumPy array. But the result that we get back again is a single answer. It's a single number that hasn't been computed yet, hasn't been calculated yet. So we can call visualize and see, this small amount of code here that feels like NumPy, actually Dask converted that into a whole mess of acyclic task graph calls. These are all the functions we need to run. These are all the bits of memory intermediate steps that we would have. Here's how we get all the way to this final number. And if I call compute, we can see, this bottom plot. I don't know why this bottom plot keeps disappearing. Let's run that again so you can kind of see. It's too fast. It's very fast. We can make this. Let's make this bigger. Let's do something more interesting. So hopefully these plots will kind of show you a bit more of what's going on, and I'll refresh them all. So let's make a really big. Let's make a reasonably big array. So this time I'm going to make an array that is 20,000 by 20,000 in chunks of 2,000 by 2,000. So this tells us here, this ran instantly, right? I'm running this because all Dask is doing is saying, in order to make an array that looks like the one that you asked for, I would need to do these steps, right? It's not calculating the array. It's just working out what it would need to do in order to calculate the array. So the array that we would get back from this operation is a 3 gig array in chunks of 32 meg. It has this shape, it has this chunk size. It would take 100 tasks to get to this point. We could do the same operation then. We just add it to its transpose equals sum. In order to get there, we would end up with a single number at the end. It would take 439 tasks in order to do this. And so let me just refresh all my little widgety panes so we can actually see stuff happening. I think it might be Binder that's like breaking my WebSocket connection and remaking it that's breaking things here. But if I call compute now on my, the graph will look very much like this, but wider. If I call compute here, we can see a whole bunch of stuff going on, right? The progress bars are starting to tick through all these different operations that need to be called. Tasks are starting to execute on the workers. We've got these sum calls. We've got these random sample calls. Stuff is swapping back and forth. But this array is 3.2 gig. I only have 2 gig of RAM on Binder. We only made a Dask cluster right at the beginning, which has 2 workers with a gig of RAM each. So we're working on a NumPy array that is bigger than memory here. And it's just, it's breaking up into pieces. It's working its way through the order of operations it needs to do. It's freeing up memory where it can. As it aggregates the answers, it can kind of free things. Calling sum. Once you've called sum, you can get rid of the array that you were summing. You can see here in the end bytes that these bars keep going orange. This is because we're pushing up against the memory limits, and it's starting to think about swapping to disk. It's trying to give you an overview of what's going on. We can see there was a bunch of chat between the two workers, and some gaps as the scheduler was having a think and readjusting stuff. But we reasonably easily there called an operation on a pretty big data set, or a data set that I wouldn't have been able to do on a 3 gig on this 2 gig machine, and I can get the answer at the end. So let me just, there's a question in the chat. So let me have a look. I think Willie's answered it actually. What order of speed up do we gain from using Dask for this more heavy load example? So yeah, as Willie said, the speed up here is probably not huge, but mainly because NumPy can do things kind of out of core as well. But say I was trying to work on a 1 terabyte array with 5 machines, right? You just can't do that in NumPy. Like NumPy can only run on 1 machine. It can only make use of one system. So as you start scaling out and adding more machines, you can work on things that are bigger than the memory of your single machine. You can work on things that are bigger than the memory of your overall cluster of machines. And you can just work on things that are not possible before. So I'm going to stop. We kind of come to the end of this array notebook. I'm going to close out my cluster again, free everything up, just have a quick look at where I am with my timings. That took slightly longer than I had intended, but I think we're still fine. Let me come in and shut down my notebook as well. let's have a look. There's a question that's come up on YouTube. If I want to do 3 tasks on the same data and task 2 and 3 are both based on task 1, would I call compute on task 1? So this kind of comes to where we've got a graph here that we can see. We have some memory here, right? Like, I don't know if you can see my mouse in the thing. There's along this bottom row, we have our random samples, and each of these outputs some memory. That bit of memory feeds into 3 separate function calls in order to do our transpose and sum and all of that kind of stuff. So Dask will know that I need to feed this number into these 3 functions, so I need to hold this piece of memory until each of those 3 functions are finished, and I've got the result out the other end. So it kind of handles swapping those around. The scheduler also does hashing on the calls. So it knows that if you read in some data in a couple of different places, and it's the same, you've read the same file, you've done the same thing, you've loaded the same stuff, you've called the same operations, it will do that and like reduce the complexity. It will reduce the operations required. Right, I'm going to move on to the machine learning example. And yeah, we'll just keep going. So we've done Dask array, we've done Dask data frame. Now we're gonna have a look at Dask ML. This is the piece of Dask that is based on scikit-learn. Scikit-learn is a nice Python library for doing kind of standard statistical machine learning stuff. This isn't like TensorFlow, PyTorch type stuff. This is, you know, linear regression, random forest kind of machine learning statistics stuff. But the idea is exactly the same. If you know how to use scikit-learn, if you're familiar with the APIs of scikit-learn, then the Dask ML tool will look exactly the same. You import a different library and it works basically the same way. You know, instead of from scikit-learn importing logistic regression, from Dask ML, you import logistic regression. The idea is the same. Scikit-learn's kind of got some stuff in it for parallelizing out with Dask already. So you can kind of come at this from either side. You can either use scikit-learn and tell it to use Dask as a backend, or you can use Dask ML, which is kind of implementing re-implementing bits of scikit-learn in Dask. There's, you know, pros and cons to each one of those. I'm not knowledgeable enough on those things to really comment, but have a look at the various bits of documentation. But there's a bunch of collaboration between these 2 communities. We know each other reasonably well, so all this stuff is kind of built together in concert. But some of these operations can scale really nicely if you have more than one machine or more than one core or whatever. And so being able to use Dask to split things up into chunks and tasks and separate them around will give you some performance increases using different techniques, I guess. Other libraries as well, like XGBoost or like GBM or PyTorch or all these other libraries are all kind of working on interoperability as well and swapping stuff around. This is kind of, you're kind of getting back into maybe towards the Rapids Nvidia kind of world as well, where you care about having data sets on GPU memory, and I want to use some machine learning, you know, tool to train some data. So I want to read in a Dask array on the GPU using CuPy, and then I want to do some operations to it to kind of clean it up. And, you know, my data's messy because all data's messy and I want to clean it up and sort it out. And then I want to hand that onto PyTorch. Can I do that in like a 0 copy way? Like all of this stuff is kind of supported. There's a lot of interoperability between these tools, I guess is what I'm trying to say. A lot of these communities are working together to build ways of swapping data between various tools without actually copying it around and calling into one tool from another tool. Anyway, let's have a quick play with the scikit-learn style API in Dask. So again, we're going to make the same Dask cluster we've made every time, 2 cores, 2 gig of RAM. We're going to read in a data set called diamonds this time. This data set has a bunch of information about diamonds. So we have, you know, this is we're back in data frame world again, right? To work through this Dask ML stuff. We have a bunch of diamonds. We haven't read them yet because Dask's doing this lazily, but we can see the columns. Each of these diamonds have got, you know, a carat and a cut and a color and clarity and all this information about the diamond. We know stuff about the diamond, and so we can do some predictive stuff around this. So let's we've got an unnamed column here. Let's just drop that for now. We can do like standard pandas statistical things, like we can call categorize on our data set to try and categorize things instead of having objects, and we can do some reshaping and that kind of stuff, right? I'm slightly out of my depth here in terms of machine learning stuff. Like I said, I mainly work on clustering and that kind of stuff, but I'm going to run through this material as it is. But what we can do is we can get information about this using, this is the pandas type functionality, right? We can grab our data, we can get more information about it, and grab categories and kind of explode everything out into columns, basically. Because what we eventually are going to want is an array that we can work on. We don't want this to be a data frame with all this kind of context and stuff. We want an array of numbers that we can feed into some statistical model. So, you know, we can do these kind of things here. Alternatively, you could use scikit-learn to do the same kind of thing, to categorize your data and break it out and stuff. But if we have a look at our prepared data, just we call a head on it, we can see we have a bunch of diamonds. They've got some data and some information. We've got some, like, you know, Boolean data about that we pulled from the categories. And then we've got like our float data here as well, like our caret and depth and that kind of stuff. Now what we can do is we can pull out we can pull out the column that we want to calculate here. So what we're trying to achieve with this is we have this data about a load of diamonds that we know about. What we want to work out is how much that diamond is worth, because that's something that's worth being able to predict in the future, right? I guess this data is based on some sales, you know, historic sales or something. If what we want to do is pull out the price column, so let's pull that out. Let's do our prepared data. We just want the price column, and let's convert that to a Dask array. So we now end up with a 1 by, you know, 5,000, 50,000 array, which is just this price column, because this is the thing that we want to work out. Or we want to build a model to predict, basically. So then from our prepared data, we want to drop this price column and also convert that into an array. So let's run the same operation. So we've now got Y, which is our price, and, you know, our array, which represents all the other attributes. And what we're going to do is we're going to use train test split, which is a scikit-learn function that's also available in Dask.ml. And we're going to split this out. So we have X train and X test, and Y train and Y test. So we're going to have some data from our, like, larger data set that we're going to train our model on. And so we're going to have that data, and we're going to have the prices, and we're going to know those things. So we can train some model to predict based on these attributes, what will the price be. And then we also have our test data sets, which are going to be like a completely separate set of data that we can use to say, you know, how good is our prediction once we built our model. If we feed in some more overall data, is it giving us the right kind of price? So I think for this example, I'm pulling out like 10% for testing. I think it's probably more relevant to pull out a larger amount, but just for this example, we'll use 10% for testing. So if we have a look, now we've got our X train and Y train. These are slightly shorter arrays. And then we're going to use a linear regression. So again, we're doing this, we're importing this from Dask.ml, but this is exactly the same as if you're going to do it in scikit-learn. It's just you'd import it from scikit-learn instead. We're going to set up our logistic regression, and we're going to fit our model. So let me just reload my frames here just to make sure, just because they keep going funny. Apologies for that. But let's reload all those frames. I'm going to fit my model now. So we're doing 10 iterations here. So we're going to iterate and try and improve our model 10 times. So the way Dask is handling that in this example is the one single train operation is being split up into a Dask graph and executed. And then when it finishes, it's starting another whole train session. So you can kind of see the progress bars are kind of loading all the way to the end and then resetting back to the beginning. That's just because we're submitting multiple things to the Dask scheduler kind of over time. And we can kind of see there's a lot of communication going on between the workers, a lot of tasks being calculated here. We're using some memory, but we're going through and we're trying to whack a straight line through a bunch of data in order to work out what our cost will be. And then we can have a look at like how good our output was. We can look at our model. We can then have a look at our test data and check, what is the mean squared error of our test data, right? So this is kind of running us all the way through to give us like a final result at the end of how good is our model at predicting something. You know, this isn't my area. I don't know how good this came out at, but the next section of the notebook is another moment where I'm going to shut up for a minute and just let you work through a hands-on lab. Now it's 25 past now. I've been going for, let me just look, 75 minutes. I expect it to be, I'm running a little bit late. What I'm going to do is I'm gonna skip past this actually, I think, just to keep going through the rest of the material. But this hands-on lab at the end here is exactly the same thing, right? We have a whole nother data set which is based on a power plant and the outputs of the, you know, how much power is output from that power plant and what are like a bunch of properties about it. What's its relative humidity and pressure and temperature, and what's the exhaust vacuum, you know, pressure and stuff. And so this lab is kind of talking you through doing exactly the same thing. So let me just pick up on a question in the chat, which says, I'm curious about the answer when defining a client, how can we find the maximum best resources we can use on a machine? So Dask will auto-detect a whole bunch of this stuff. I'm actually about to, I'm going to come to this in the distributed section, basically. We're going to talk a bit about how clusters kind of pull together and how we set things up. Basically, it can work it out on its own. I've explicitly told it for this session just because I thought being explicit for a tutorial would be useful. But if you just tell Dask, make me a cluster, it will inspect the machine, it will work out how many cores there are, it will work out how much memory there is, and it has some built-in kind of decision-making for how to break things up. So we'll kind of come onto this in detail in a bit, but yes, you don't need to worry about that yourself ahead of time. So let's close out my cluster again. If you want to run through this hands-on lab in your own time, this binder is always available. This repo is kind of always here, so please do. But I'm going to move on. I'm going to skip over to the 7th notebook, where we're talking about some kind of underlying things. So let's just shut down that. Discard that. So yes, let's keep going. Everything we've done so far has been about using APIs that will be familiar to you if you're familiar with other tools, right? If you're used to Pandas, this will be familiar to you. If you're used to NumPy, this will be familiar to you. If you're used to scikit-learn, this will be familiar to you. But all of that is using underlying primitives in Dask that handles all of this kind of distributed computing. So I'm probably going to go through this reasonably quickly to get onto the actual cluster management stuff. But this is kind of pulling us all the way back to the beginning when David gave his introduction of building up graphs of things and executing tasks. So let's kind of dig in a little bit here. There's a question just about the previous section. So just say, what was the advantage of doing ML in Dask versus scikit-learn? Is there a speed up? So yes, the answer is yes, there is a speed up. In scikit-learn, you're limited to the machine that you're on. Whereas if you have a Dask cluster of 10 machines, the performance should increase. You know, there are upsides and downsides to distributing things, but if you're doing something like a linear regression or something, then yes, having more computers involved in that operation will give you more performance. Okay, bags features and some bonus features. So let's make ourselves another cluster. Now specifically this time I've done almost the same thing, but with a smaller memory limit. Now I haven't looked at this tutorial for a little while, so I can't remember why, but there will be a reason, and I'll come on to that in a minute. So Dask bag is another data structure inside Dask, kind of similar to data frames or arrays or whatever, but it's more like a collection. It's more like a list in Python. Now, you know, sometimes these are useful, but we're just gonna have a quick look at also using Dask bag. So we can import from Dask bag, we import it as DB, and we can create ourselves a bag from a sequence. So we can say, here's a list. This is actually a generator, right? But we say, here's a list of stuff. Please give me a bag which represents this list of stuff. And we're saying 4 partitions here. So this is the opposite of what we had last time, where this one we're saying, break this into 4 pieces. We're not saying pieces of 4. So there's a slight difference between the array API and the bag API. But we have this bag which has 4 bits in it. We can count those bits and compute the answer. We say, well, if you sum, doing count on a bag like this is the same as doing a sum on this range. But again, these 4 partitions are separate tasks, they're separate pieces. They can be distributed onto separate machines. They can be swapped in and out of memory, all that kind of stuff. We have a look at M partitions, we can see there are 4 partitions. They don't have to be in the same place. We can do different kind of stuff. Bags, you can do stuff like map a function over that bag, so we can square everything. We pass it like a callable, like a lambda. We can map over the elements in our bag. We can't directly index into our bag because the order is not guaranteed. So instead we can call take, which will take 5 items from our bag. I think this will probably give me an ordered thing just to prove me wrong, but like the order is not guaranteed in a bag. You can do kind of normal kind of listy countery operations with bag, and Dask will distribute it for you. So I'm kind of rushing through this a little bit because I personally don't tend to find bag particularly relevant. Sometimes I found it really useful. Say I have like a really long list of files maybe that I want to read in, and there is no like file reader in Dask for reading that file type. So maybe I need to, but maybe I have a file reader that can read to NumPy. I might make a bag of all the file names and then map the like read file call across the bag, which will give me then a bag of NumPy arrays, and then I can convert that bag into a Dask array, right? So it can be useful in that operation, right? Like a list of file names is something you would put in a list, right? But you can distribute that across your cluster. That tends to be the only time I've kind of used this, but you can kind of do these kind of operations. I'm just stepping through to make sure everything works here. So feel free to dig more into that documentation, but I personally haven't found it's come up a huge amount. Dask delayed is the building block of everything in Dask, basically. So let's spend a little time thinking about this. Most of the time, you don't have to care about it, but this is the idea of doing things lazily, doing things just in time. What we do in Dask is we delay stuff into the future. So we have Dask delayed and we have concurrent futures, which is like a built-in Python thing. So let's start with a little toy example of doing some function calls. And this is maybe something that doesn't fit into the array or the data frame or the scikit-learn paradigm. Maybe I just want to write some bespoke Python for some reason. This is how you can do it in Dask world and deal with it yourself. So let's say I want to, I'm going to mock out some expensive operations by doing some simple operations and sleeping, just to make it pretend like it's harder than it is. But let's say we have a few functions I've defined. We have increment, which is just going to add 1. We have double, which is going to multiply by 2. And we have add, which is going to take 2 numbers and add them together. So if I define my functions, each one of these is going to sleep for half a second. Now, if I have another cell where I make myself a list, there's no Dask here yet. Okay, I'm just doing some pure Python. If I have a list, and I have like an output array, maybe I want to loop over my items in my data, and I want to increment each item, and then I want to double each item, and then I want to add those 2 things together, the incremented number and the doubled number, and then I want to add those onto the end of an array, and then I finally want to sum all of those things. I can do that, right? There's kind of standard Python things. If I run this is just running on 1 core of my binder instance. It's just doing something in pure Python. And this took 6 seconds. That's because we've got 4 numbers. So we had to do inc and double on each of those numbers. So that's a second for each one. And then we had to add those numbers as well. So we get another 2 seconds on that. And then we had to sum, right? So we've got 6 seconds altogether of running this kind of thing. But these operations could be parallelized, right? These things don't have to happen in order, right? Inc and double could happen at the same time, and then they both feed into add. So what we could do is we could Daskify this workload to make things happen concurrently. So it should go faster than 6 seconds. So let's import Dask delayed. Dask delayed is a decorator. A decorator is like a way of modifying a function, basically. So there's a couple of options. We could either we could either define our increment function and you know, it does whatever, and we decorate it and we say this is delayed like that. Or we can take an existing function and we can call delayed on it to give us like a delayed version of that function. So I'm going to call this lazy increment. And so we've taken our simple increment function from here, and we've called delayed on it to give us a lazy increment function. So if I run this, now if I do you know, lazy increment 3 instead of increment 3, this will give me back a delayed object, right? Instead of giving me back 4, which is what inc would give me, it gives me a delayed thing. And this is kind of this is a future, right? This thing will be done at some point in the future when you need it. And these are the building blocks of our graph that will feed into each other. So this is Dask basically saying, when you need me to, I'll call inc, but in the meantime, here's a placeholder. It's this thing here. And this is like a hash of that call. And this is where I said earlier that if Dask finds multiple hashes, it will like consolidate them down. This is kind of how it does it, is down on these delay functions like this. So if I now visualize my operation, I have a single function call, which is inc, which takes in some input from me, and it gives me back an answer, which is the incremented answer. And I can call compute exactly as we've done before, and it'll give me the number 4, right? So this is me explicitly saying, okay, please execute my extremely trivial graph to give me my answer. So that's great. But now we can start thinking about chaining these together. So let's have a double inc. So we're going to call lazy inc on inc output, right? So we've incremented it once lazily, then we're going to increment it again lazily. So this will give us back another delayed object. And if we visualize this, we can see our task graph is starting to build now, right? We're incrementing once, we get some memory, then we're going to increment again, we get some memory, and we can call compute, we should get 5. I've got like a phone as a stopwatch here and it's just slid down. There we go. We get 5, right? So that's great. We can start building up lazy distributed code. So now let's redefine everything. Instead of kind of doing all this assignment stuff we've been doing, let's redefine inc, double, and add, and we're going to decorate them with delayed. So we now have, these are the same functions as before, but they're now all delayed. And so we can take exactly the same code we had before, basically, where we have our array of 1 through 4. We have our output. We're going to run through each of our operations. We're going to call inc, we're going to call double, we're going to call add, we're going to append those to C. We're also going to take the like built-in Python sum and say, well, I want this to be delayed as well. And we're going to immediately call that. So we're not actually reassigning that. We're just going to say, please do a delayed sum of our array to give us our total. So if I now run this and time it, that happened like instantly, immediately, because nothing's happened. Dask is being lazy here. It has worked out what that graph looks like very quickly and given us back a delayed object that represents what the total answer would be if we computed it. But this means we can look at the graph. So if I call visualize now, we can see, you know, we're going to take in the number 1, we're going to increment it and double it and then add those together. We're going to take in the number 2, increment double and add them together, and so on. And then once we've added those numbers together, we're then going to do a sum where we pull like everything together in like a reduce, and then we finally get our answer, right? So we've taken some Python code that looks like nice normal Python code, and we've turned it into this lazy delayed code. But the nice thing about this is we have this graph representation. We know how to call this. We could now call this on many machines. We could have 1 machine per function. In this example, I have 2 cores on Binder, so I'm going to use both of those. So if I call compute now on this and time that, I don't know if my dashboards have gone a bit stale. Oh, the cluster map's doing something. We get the same answer we got before, but this time it took 3 seconds instead of the 6 seconds that it took before up here. And that's because, all the same sleeps happened, all the same things happened at the same time. It's just that some of those sleeps happened concurrently, right? These increments and doubles, they all slept at the same time. Well, 2 of them slept at the same time because the workers were dealing with 2 at a time. So things went twice as fast because we have 2 workers. If we have more workers, things will go even faster because we can get more parallelism. This is a nice example of where the things that's blocking us is not something that's actually like, we're not computationally bound here, we're sleeping, but maybe this is IO, or maybe this is some other operation where our machine is just waiting. So instead of, waiting sequentially, let's wait in parallel and get some performance increases here. Now, these future objects, we can visualize them and compute them. We can also, get their type, and we can play around with them and do all sorts of other stuff. But I'm going to leave you to look through that kind of in your own time. But you can get the result of them and that kind of stuff. But I think we've seen basically everything we need to see here. So I'm going to close out that cluster, and then shut down my notebook, and I'm going to move on to the last piece that I'm going to talk through here. Let me just remind myself what's in the wrap up. No, that's for you. That's fine. Yeah, this is the last notebook that I'm going to run through, which is the distributed notebook. And I'm going to dig a little bit into the Dask clusters and how they work. I just want to check. It is now 22. I think this session ends on the hour. I've intentionally gone a little slow because this tutorial is normally 90 minutes, and we had a 2-hour slot. So I'm going a little slow. I've maybe got 10 minutes worth of material left. Can I just check with the other organizery folks if that's okay if I run up for another 10 minutes?
Absolutely. We don't have a hard out, I don't think, Alan, right? I'll check Alan on that. But
no, it's fine. Yeah, go ahead.
Cool, perfect. All right, well, I'm probably going to run on for this for another 10 minutes, and then I'll stick around for another 10 minutes after that, just to take any more questions and that kind of thing. So let's dig into distributed. Every time I've made a cluster in here, I've used the Dask client to make me everything that I need. And I've been a little bit explicit about how I've made it, but there are loads and loads of options of how you can pull these things together. So all that we really care about here in order to distribute our work is we have to have a scheduler that's going to keep track of all of these tasks, what's run at what point, what memory is where, what needs doing in order to get the result. We then have workers, right, which are all these components that are actually executing our code. And then we have our client, which is the thing that we're kind of connecting into the cluster in order to submit work via. So we have these 3 different types of piece. And in Dask, if you have nothing, right, if you're just starting from, I've just installed Dask on my machine, if I import client and make a client, but don't tell it what to connect to, Dask will figure everything else out. We'll go, right, well, you've not told me to connect to a cluster, so I need a scheduler and I need some workers. I'm going to have a look at your machine. Oh, you're on a laptop with 12 cores and 16 gig of RAM. So I'm going to make 4 workers, and I'm going to give them, it's going to split all your resources up. It's going to work out what you need. And it's going to give you a little cluster, and then you can go and do all of the workload that we've been doing in these notebooks on your single machine. And it's been very clever about that, and it's kind of hidden some stuff away. So let's unpackage that. What's going on? What are we doing? So the first place I want to start is in distributed, we have this class called local cluster. Now this is what we refer to as a cluster manager. There's a whole bunch of these, and I can spend hours talking about them because these are the things that I tend to build. But cluster managers are classes which represent a scheduler and workers on some platform. So local cluster represents a scheduler and workers on the local machine. But if you're a Kubernetes user, then there's kube cluster. If you're an HPC user, then there's various clusters in Dask job queue, like you've got PBS cluster and Slurm cluster and SGE cluster and things. If you're a cloud user, then we have Dask Cloud Provider, which has got a Google Cloud Platform cluster and an Azure cluster and an AWS cluster. And we've got a whole bunch of cluster managers. They handle the life cycle of creating a scheduler, creating workers, and they can also, depending on your platform, they can add and remove workers as required. On a local cluster, that doesn't make sense because I can't add and remove cores to my laptop on the fly. But on the cloud, I can just ask Amazon for more machines and I will get more resource. So I can adaptively scale as well. But when we called client previously, that noticed that we didn't have a cluster and made one for us. So what that actually did is it called local cluster under the hood. So let's have a look at local cluster for a second. Let's import both of these things. If I do cluster equals local cluster, I think this answers one of the questions that was asked before as well, is local cluster will inspect this machine and say, what is this machine? What can I have? And when I run this on Binder, it says you have 1 CPU core and 2 gig of RAM. So actually this whole time, I know I kept saying we have 2 cores and 2 gig of RAM, but that's just because I wanted 2 workers. We actually only have 1 core. I was kind of just relying on the threading. There probably was some contention in everything we've ran before, but it's fine. But local cluster here has detected what resources we have on our machine. If I run this on my machine, my laptop, I get 12 and 16. If I spin up some nice big machine on AWS, I might get 24 and 96, or it will just look at the machine and work it out. I think we have some heuristic which tries to split up the number of workers and cores. So like a worker can have more than one core. It can be thinking about more than one thing at a time. But we tend to have, on a large machine, we tend to have multiple workers just to handle failure a bit better. If the actual worker itself dies for any reason, we don't want to lose all of the work on that machine. So I think on my 12 core machine, I think I get 3 workers. I get 3 workers with 4 cores each or something. But this is built into Dask. It works out these things. It knows kind of some best practice. You can fiddle with these things if you want to. This local cluster object also tells me where the dashboard is. Now things aren't very well configured on Binder. So it's just pointing me to localhost, but this should be pointing me to my thing. So yeah, Willie's just said, note of caution for HPC users, local cluster will think the whole shared front end is yours. Yes, so if you run local cluster, generally, right, you run stuff from a login node on an HPC. So if you run local cluster from wherever your login node is, you'll take over the whole login node, but not any of the HPC, just the login node. So it's worth kind of knowing where you're running stuff from. We also have some widgety things which are helpful here. We can manually scale. I think I can actually manually scale. If I click scale, it's going to make me another worker. So I'm just like oversubscribing this Binder instance now, but it's just made me a new worker. It started a new worker process. Let's scale that down again. And we can do adaptive scaling as well. So we can say, well, I want a minimum of 1 worker and a maximum of 100 workers. And it will sit at the minimum until you submit some work to the scheduler. And the scheduler has some more built-in heuristics that try and work out how many workers would I need in order to execute this whole graph in 5 seconds. So it starts running some tasks and profiling them, and then it starts asking for more workers to try and speed up. So this can be really useful on a platform where you can get allocations very quickly. This might not necessarily be so useful on HPC if it takes a long time to get allocations. It just depends, machine to machine, right? Like if you've got very fast, snappy, responsive interactive queues, then it can be quite nice for submitting some stuff. If you're on the cloud and you can grab resources very quickly, that's great. But if you're on something where you have to wait a few minutes per, to get an allocation filled, you might want to start like a fixed size cluster or manually scale before you do some work. So let's have a look at some of the configuration that you can pass to a local cluster. You can set all sorts of stuff on here. You can set where these dashboard addresses are and where the worker addresses are, host and IP, ports and all that kind of stuff. All of these things are actually what we passed through client before, right? We said how many workers we want and how many threads per worker and what the memory limit is and stuff. These actually were options on the local cluster, and client was being friendly and forwarding them onto you. So, you can spin up local clusters. Then you could do really useful things with that cluster object. Like you can get the logs of the cluster. So we can see, cluster doesn't matter at the moment, but the scheduler, we can see, oh, this is the logs from the scheduler process. So we can see the scheduler started and this is its address. Again, we're in Binder. We only know about ourselves at the moment, but we can see our worker registered. We did some work. And we added the other worker when I scaled up. And that became ready. And then I removed that worker again, right? We can see what the scheduler's done. And we can also see our one worker that we still have. We can see that worker's log as well. So we can see, the worker has started up here, and I've registered myself to the scheduler here. So this is really useful if you're running stuff with Dask. Sometimes if you get exceptions on the worker, a lot of the time they'll bubble all the way back to you and you'll see them in the client where we are. But sometimes you don't, right? Especially if you're missing libraries. If you when you run clusters like this, you need to ensure that the Python environment is consistent between the client and all of the workers, which is usually fine on an HPC system because you're probably using module or something to load in some consistent environment or Conda. But maybe I'm on my laptop and I want to connect some cluster in the cloud. My laptop's environment might be slightly different to the cloud. And so if the workers are missing a library that I have locally and I use it, sometimes they may throw an exception and kind of die. So you can come in here, you can get the logs and you can have a look and you can see, oh, look, this worker died because of this reason. It has other kind of useful things like getting the dashboard link. Again, I said this is wrong because I haven't configured Binder correctly, but on maybe an HPC system, this might tell you the right URL. Then one of the really useful things about these cluster objects is you can set them up, you can configure them, you can do whatever. Local cluster is very simple. There's also, if you're on the cloud, you might want to set VM types and sizes and operating system images and all that kind of stuff. You do all of that when you construct the cluster object. And then you have this object that you can do stuff with, getting the logs, but you can also make a Dask client from that object. So you can just say, make me a client, here's a cluster, and Dask will work out how to connect to it, how to open communication. And once this client object exists, work will start being submitted to the cluster. That's how Dask knows to do these things. Let's just delete both of those. Now, I think last time I ran through this, things maybe seemed a bit broken. I don't know whether Binder changed or I changed or something. But let's talk about another very common, this is the most common way of deploying Dask onto multiple machines, especially when you're getting started, is just via SSH. If you have access to a bunch of machines, so I used to do this in my previous job where I sat in a large office with a bunch of folks with Linux workstations, which is weird. That feels like a long time ago, given everybody's at home now. But I sat in an office with a bunch of folks with Linux workstations. We could all SSH into each other's workstations. It was actually really funny if folks went to lunch or something and their machines weren't doing anything. I could use Dask, SSH into a bunch of machines and grab all of those resources together into a little cluster to do some fast work. You can either do that by literally SSHing and running the Dask scheduler and Dask worker commands, or you can use this kind of convenience cluster manager. So you say, I want to create a cluster. Here's a list of hosts to connect to. I'm just, in this example, I don't know if this will work because I think Binder might have broken this. Let's see. It doesn't seem to be doing anything, so I think things may be broken. But what we're saying here is, oh, maybe it did work. Okay, that's good. So what we're saying is SSH to these three places. The first one, start a scheduler, and the other two, start workers and connect those to that scheduler. So in this case, I'm just SSHing to localhost over and over and over. But in reality, you would SSH to other things. Maybe you would run a scheduler running on your workstation and maybe a worker running on your workstation. So you might have like two local hosts, and then you have a bunch of other workstations you have access to, or a cluster of machines or whatever. You put in the host names of those, it will create you a cluster object, and everything will be kind of pulled together. You can see it's actually detected the IP address of the machine. Again, this doesn't make sense because it's in Binder, but in a real network, this link should work. And then we could create a client from that and basically make use of a bunch of resource via SSH as well as other things. So there's a bunch of links here to kind of Kubernetes support, Hadoop support, cloud platforms, batch systems, HPC, all of that kind of stuff. There's cluster managers for all of these things. You can scale them, you can adapt them. There's also a blog post that I wrote a little while ago on the Dask blog that I kind of want to just point you at as well, just to kind of cap off this section, which is the current state of distributed Dask clusters, which I wrote in the summer, but it's still pretty relevant. And it kind of walks through all the different cluster managers that you have, Kubernetes and Helm and JobQ and all these kind of things, giving you examples of how to deploy Dask, how to set up these clusters on various platforms. So, I recommend you go and have a look at that if you have some time. And the last thing to kind of touch on here is everything we've spoken about up to this point is all very user-centric, right? This is how you can deploy a Dask cluster. Here's how you can, if you have access to machines, you can leverage those and pull them together and run workloads on them. But if you're maybe in a position where you manage a team or you manage resource for a team or a department, there are other tools around there that allow you to like centralize, authenticate, federate the construction of clusters. So Jupyter Hub in the Jupyter community is one of those tools where you can kind of have a web page, you log in, you click, I want a Jupyter notebook. Maybe it launches a notebook onto an HPC system and proxies the connection back to you. It's a popular tool within a bunch of places. Dask has an equivalent service called Dask Gateway, which is like a central service which knows how to talk to Kubernetes. It knows how to talk to various HPC systems and Yarn Hadoop systems. And it can create Dask clusters on your behalf. So maybe you're in an organization where you don't want to let people spin stuff up on various clusters. Maybe you just want to centrally manage things. Dask Gateway is a good way of handling that, adding authentication and trying to reduce effort. So if you're interested in how can I provide Dask to my team without them having to worry about any of this cluster stuff, Dask Gateway is a good thing to go and look at. So that's it. That's the end of my rambling and waffling. There's a best practices notebook in here as well, which has just got some kind of recap on some of the things I've said, some links to some of the bits of documentation. But yeah, basically that's it from me. I hope this has been a useful session. And thank you very much for paying attention and sticking around.
Thank you very much. Do we have other questions? We have had a few in there. Billy, was there anything else that should be answered that you caught?
No, maybe there were a few questions. I'm not sure if I really understood them correctly, but they were about, couldn't I also slow down stuff if I chunk things? And I think that's worth mentioning. Dask doesn't always give you a speed up, right? So you can, especially if you chunk stuff, if you split stuff with Dask, that could have easily done in memory and with the available CPU in NumPy, then you can add basically arbitrary overhead by building a huge graph that essentially does the same thing that NumPy could do in one step. So
yeah,
usually
that's absolutely
worth,
true.
Usually it's worth considering what limit you want to leave behind, right? Are you CPU bound? Are you memory bound? Are you IO bound? There's a whole bunch of problems where you can profit from scaling out to many nodes because you're on a distributed file system, and then really consciously decide to use Dask in the way you use it. Just using a Dask cluster and then typing ahead probably won't you get into big trouble, but it's not always guaranteed to speed you up in any way.
Yeah, I wouldn't recommend like everybody switching from NumPy to Dask array and Pandas to Dask data frame just as standard, right? It's kind of use it when you feel like you know, you're bound by one of those things that Billy mentioned.
And then there was a question by Alex, which goes probably to me about the next seminar. So what topics are we gonna talk about in the next seminar? I think we'll present some easy to grasp and at least close to real world workflows on an HPC cluster using Dask job queue, which is using, in our case, one cluster manager class that can scale out Dask workers or Dask clusters to many nodes or jobs on an HPC cluster using Slurm in our case, but there's many different cluster managers for other batch schedulers. So we'll have one or two relatively easy to understand, mostly Dask array-based examples, and then get into all kinds of techniques of how to adapt these clusters to the actual workload, how to scale these clusters, how to choose a good ratio between processes and threads for different applications, how to leverage many processes for improving I/O performance. If you are in a world where I/O is not thread safe and artificially serialized, etc. And so I think the Dask specific stuff will be relatively easy. We'll just see a bunch of ways of creating Dask clusters and have a relatively easy application that I hope everybody will understand in 1 or 2 minutes. But then we'll have lots of different ways of speeding up or slowing down stuff by choosing cluster layouts and also Dask array chunk layouts.
And that will be on the 4th of February, right?
Yeah.
I'm going to take a organizer's prerogative to ask Jacob a question. One of the things that you went through pretty quickly, the delayed versus the futures-based API. Any advice on when to use one over the other?
I mean, so those are delayed and futures are like complementary parts within Dask, right? Like Dask supports, Python's kind of standard futures, and everything kind of builds around that. So the idea of delaying your function calls is a way of converting your operation into a future, right, to work on. But the Dask delayed objects just kind of have like a slightly larger API. It provides you like a little bit more feedback on that. But yeah, it's if you want to write stuff and handcraft yourself, then Dask delayed is the way to go. There's been another question in the chat just about when should you choose the Dask bag collection. As I said, kind of when I was working through that, I very rarely have to use it. I would probably only choose Dask bag when you have a list that doesn't make sense to have in any other format, or maybe you need to like bootstrap something. So loading data, I tend to find like if my input is a list of file names, especially if my input is a list of file names that I have to generate, right? So I know I've got 10,000 files. This is what I used to have in weather and climate, right? I know I've got 10,000 files. I know they will have these names because they're named by date, and I want to load some period of data. Like the first thing I'm going to do is, I don't want to put those 10,000 file names into my code. So I'm going to write a small function which generates my list of file names. And then the next step will be, lazily load each one of those using some delayed call. And then I want to convert that into the actual Dask object that it represents, right? This is often true often useful if you need to do custom loaders because you work for an organization that has proprietary file formats or something. So that's basically the only instance where I've used Dask bag. It's like, oh, I've written this function which generates these file names, but the file name list that it generates is massive, and actually I want to break that out. And also I want to break that out into pieces which will then be loaded in a distributed way. So if I'm kind of starting off with that list already distributed, it makes it easy to move the next step to like a list of distributed chunks as well. But yeah, generally I would only use Dask bag if NumPy or Pandas don't fit your use case, which is pretty rare, I think, these days.
I think with that, we have all of the questions that anyone has. I don't see any more coming in. Again, thank you very much, Jacob, and also Vili for doing this for us. I'll also say to all of the people who are watching that if you want to still sign up to get notifications about the upcoming events, please do. The links are down in the YouTube thing. That is, if you're for people on YouTube, you can go to the CCAM workshop link, and that will give you more information. And we'd be happy to have you participate in the next few, which we'll be talking more about specifically how.
So with that, let's thank Jacob and Vili, and thank you all.